This is Vector Calculus, Lecture 5. And that remind you that next Monday is President's Day. The university is closed, so there's no class next Monday. Our next class is next Wednesday. But next Thursday, we follow a Monday schedule. So we actually have a lecture next Thursday as well. So next week is a little bit strange. There are two lectures, but they're Wednesday and Thursday instead of Monday and Tuesday. So let me just remind you about all of that. And what we've been studying is chapter 13. And the last section in chapter 13 is what we do today. So chapter 13 is vectors in the geometry of space. And let me just review a little bit what we've been talking about. So in section 13.1, it is just the introduction to vectors. So you might have a vector v in three-dimensional space, which is given by its coordinates, x, y, and z. And if we have a second vector, v prime, with coordinates x prime, y prime, and z prime, then you add them by adding coordinates. And this is geometrically described very nicely in three-dimensional space. If this is the vector v, and this is the vector v prime, this is the origin. It's as if you could draw, well, you can draw a parallelogram, and the opposite vertex, the vertex of the parallelogram, opposite from the origin, is the sum of the two vectors. So this is sometimes called the parallelogram rule for vector addition. And if you take a scalar c, scalar is just a number, it's just another word for number, c times the vector v, that's c times the vector with coordinates x, y, z, is the vector you get by multiplying each coordinate by c. And this just corresponds to stretching the vector by a factor c. So this might be c times v if c is positive. If c were negative, it would go off in the opposite direction. And if c were zero, it would just be the zero vector. So if you have the vector 1, 2, 3, and you multiply it by 7, and you subtract the vector 4, 5, 6, multiplied by 2, what do you get? 7 times 1, 2, 3 is 7, 14, 21. 2 times 4, 5, 6 is 8, 10, 12. And when you add, you get 15, 24, 33, if I added correctly. So that's just a simple operation on vectors. And the magnitude, which is the same as the length of the vector v, is you write v with absolute value signs around it, and it's really just the Pythagorean theorem. It's the square root of the sum of the squares of the coordinates. And v is called a unit vector if the length of v is 1. And we defined the dot product and the vector product of vectors as follows. So you have the dot product of two vectors. U and V. So let's write it as U dot V. And this is, so here's the vector U, here's the vector V. Whether they're in two-dimensional space or three-dimensional space, two non-parallel vectors define a plane, there's an angle between them, and you take the acute angle between them. I mean, you could take an angle like this, but you choose the angle between 0 and pi. And this is defined to be the length of U times the length of V times the cosine of the angle between the two vectors, where you choose theta between 0 and pi. And we say that U and V are orthogonal, which is another word for perpendicular, and sometimes normal, if U and V are non-zero vectors and the dot product is equal to 0. Of course, the dot product is the length of U times the length of V times the cosine of the angle between them. And a vector is non-zero if and only if its length is non-zero. So the only time two vectors are perpendicular is if the cosine of theta is 0. And the only angle between 0 and pi whose cosine is 0 is pi over 2 radians. So that means this angle is a right angle. It's exactly what you think it should be. And what is, and again, this dot product has simple properties like distributivity, U times V plus W, dot product is U dot V plus U dot W and so forth. There are lots of such properties. But what's very interesting is to use the dot product to solve the following problem. Suppose we have a vector V and a vector U, and we would like to decompose U into two pieces, a part that is parallel to V and a part that's perpendicular to V. So the part that is parallel to V, this we would call the projection of U onto V, or the orthogonal projection of U onto V. And if this angle is theta, and if we look at this triangle, this is a triangle. Let me just draw this as a right triangle. This is the angle theta. The length of this side of the triangle is the length of the vector U, and the length of this is what we want to find out. This is the projection. And so we know that the projection, whatever the length of that is, divided by the length of U, this is by definition the cosine of theta. In a right triangle, the cosine of an acute angle is the adjacent side divided by the hypotenuse. So this projection, which is what we want, is the length of U times the cosine of theta. Now, the length of U times the cosine of theta is almost the dot product. If I write this as the length of U, length of V times the cosine of theta, course, if I stick this length of V in, I have to divide by it. So this is an equality. And what this then is the dot product of U and V divided by the length of V. So the length of the projection of U in the direction of V is the dot product divided by V, which, yeah, that's what it is. And but this is a vector in the same direction as V. So what is a good way to write this? So the projection of U in the direction of V is, the length of it is U dot V, that's a number divided by the length of V, but it's a vector pointing in the direction of V. So if I take a unit vector in the direction of V, which is the vector V divided by its length, that is the projection. And so I can write this as U dot V over the length of V squared times the vector V, or U dot V divided by V dot V, because the dot product of a vector with itself is the length squared times V. So again, this is all review, but these are basic facts about the dot product that's important to know. So, and this is really very important. So I have a vector V, a vector U, and I want to find the projection, it's a vector, the projection of U in the direction of V, and that's the dot product of U and V divided by the dot product of V with itself times the vector V. And what is this component? It's this plus this equals this. So this is the projection of U in the direction of V. So this perpendicular piece is going to be U minus the projection of U in the direction of V. So we can decompose a vector with U with respect to V as a vector parallel to V and a vector perpendicular to V. And in fact, if you take the dot product of this with V, what do you get? You get U dot V minus the projection of U in the direction of V dot product with V. This is U dot V minus U dot V over V dot V times V dot V. These cancel, and then these cancel, and you just get 0. So that really is this decomposition. So for example, if we take U to be the vector 4, 1, and V to be the vector 3, 4, so here is the vector V, 3, 4. The vector U, 4, 1, is over here. And what is the component, what is the projection of U in the direction of V? right? This is the projection. So this is u dot v over v dot v times the vector v. The dot product of u and v is 3 times 4 plus 1 times 4. The dot product of v with itself is 3 times 3 plus 4 times 4 times the vector v. This is 12 plus 4. This is 16 over 25 times 3, 4. So that's equal, well, that's what it is. That's 16 times 25 times 3, 4. Or if you wanted to write it out completely in coordinates, this is 48 over 75, 64, sorry, 48 over 25, 64 over 25. That's what this vector is. And this component, this orthogonal piece, you take
And then
u minus the projection of u in the direction of v. U is the vector 4, 1 minus 48 over 25, 64 over 25. So 4, 1 is the same as 100 over 25, and 1 is the same as 25 over 25. Minus 48 over 25, 64 over 25. This is equal to 52 over 25 minus 39 over 25. If I did my arithmetic correctly, which you never know. Any questions about this? This is a basic calculation, and in a month or so, when we have the midterm, it's very likely that there will be a problem like this on the exam. Okay. Now, in three-dimensional space, we also have the cross product, which is sometimes called the vector product of two vectors. So if we have a vector u and v, the cross product u times v is a vector v whose length is the length of u times the length of v. Now for the dot product, we had the cosine here, but for the cross product, we have the sine. So you have vectors u and v in three-dimensional space, and an angle between them. Two vectors determine a plane, so this angle is well defined. Theta is between 0 and pi. So that's the length of this vector. And the direction of u cross v, because this is a vector, is obtained by what's called the right-hand rule. This is going to be the cross product is a vector perpendicular to u and v. So if you look at the plane that these two vectors form, the cross product is going to be perpendicular to that. It means perpendicular to both of these vectors. And the important way to calculate this is as follows. If u has coordinates u1, u2, u3, and v has coordinates v1, v2, v3, then the cross product u times v is formally computed as a 3x3 matrix. You write I, j, k. I, j, and k are the unit vectors in the x, y, and z directions. u1, u2, u3 is the second row, and v1, v2, v3 is the third row of this matrix. And this is interpreted as, if I take, for I, you take the 2x2 matrix, you get by deleting the row and column that I are in. So that's u2, u3, v2, v3. alternating signs minus U1, U3, V1, V3, J plus U1, U2, V1, V2, K. So you've had ample opportunity in the homework to do calculations with the cross product. But it's a basic thing to understand. Okay. Any questions about this? This is all, we're just kind of reviewing the chapter quickly. Okay. The next thing we looked at last week were lines and planes in space. And so this was section 13.5. Lines and planes in space. So we have our three-dimensional space, and a line, well, there's several ways to describe a line. You might know a point on the line. So you have some point. So this is for lines. So you have a point, say P0, with coordinates x0, y0, z0. This is a point on the line. And you have a certain direction. So your direction is a non-zero vector, v, say with coordinates a, b, c, which describes the direction of the line. So if, for example, this is the vector v starting from the origin, here is the point P naught, your line is going to be parallel to v going through P naught. So a point on the line will be P naught plus some multiple T times V, or if we call this the vector R naught. So R naught is the vector from the origin to that point, and a point on the line R will be R naught plus T times V. So, and if we write that in coordinates, so R, let's say, what is the point corresponding to this scalar T? And we often think of this as scalar T is time. It says you have a point in space and its position at time T is given by this formula. So this is R naught plus T times V. R naught has coordinates x naught, y naught, z naught, and V has coordinates, this is x naught, y naught, z naught, and V has coordinates a, b, c, so this is x naught, y naught, z naught, plus AT, BT, CT. So when you add, this is x naught plus AT, y naught plus BT, z naught plus CT. So this, we get what are called the parametric equations of the line. At any time t, the coordinate of x, the x coordinate is x of t equals x naught plus AT. The coordinate of y at time t, y of t, is y naught plus vt. And the coordinate of z at time t is z naught plus ct. So these are the parametric equations of the line. So in vector form, this is the equation of the line, and the parametric form is this. So to describe a line, you need to know one point on the line and the direction the line is going in. Now, they teach you in school correctly that 2 points determine a line. So suppose you have a point, say P naught, with coordinates x naught, y naught, z naught, and another point P1 with coordinates x1, y1, and z1, and you want to find the line through these 2 points. Well, we need to know the direction vector and a point on the line. Well, we have 2 points on the line. Let's just say pick this one. Well, what is this vector? So this vector, the direction vector, is just the vector from P naught to P1. So that's the vector V. The vector from here to here is coordinates x1 minus x0, y1 minus y0, z1 minus z0. So this is the A, this is the B, and this is the C. This is the direction vector of our line. Any questions about that? That's a line. I mean, the whole point of this chapter is to try to understand geometrical objects in 2- and 3-dimensional space, and the simplest is a line, and the next simplest is a plane. So planes in 3-dimensional space. So there's several ways to define a plane. We need to pick one as our starting definition. And the one that we pick and the one the book uses is the following: a plane in 3-dimensional space. So given a point P naught and a non-zero vector n, which is we call the normal vector. Remember, for a line, we had a direction vector, a point and a direction vector. For a plane, we have a point and a normal vector. So with this, we obtain the plane through P naught. So the plane through the point P naught is the set of all points P such that the vector from P naught to P is perpendicular or orthogonal or normal to this vector n. So picture looks like this. You're in space. You have some point P naught. You have some vector n. And you're looking for all points P such that the vector from P naught to P is perpendicular to n. So if P naught has coordinates x naught, y naught, and z naught, and P has coordinates x, y, and z, the vector from P naught to P has coordinates x minus x naught, y minus y naught, z minus z naught. And if n has coordinates a, b, c, and n is not the zero vector, it's not 0, 0, 0, then to say that these two vectors are perpendicular, P naught P perpendicular or orthogonal to n, means that the dot product of these two vectors is 0. And the dot product is A times x minus x naught plus B times y minus y naught plus z c times z minus z naught equals 0. So this linear equation is the equation of a plane. You have an equation that looks like this, where A, B, and C, some of them can be 0, but all three cannot be 0. This is the equation of the plane passing through the point x naught, y naught, z naught with normal vector ABC. And you can expand this, you would get AX plus BY plus CZ equals AX naught plus BY naught plus CZ naught. If I call this number D, it's AX plus BY plus CZ equals D. And in fact, any equation of this form defines a plane in three-dimensional space. So let's do a couple of calculations. Suppose we want to find the equation of the plane passing through the point P naught with coordinates 2, minus 3, 4, and normal vector n equal minus 1, 2, 3. So what is the equation? It is minus 1 times x minus 2 plus 2 times y minus minus 3 plus 3 times z minus 4 equals 0. That's the same as minus x plus 2 plus 2y plus 6 plus 3z minus 12 equals 0. Or minus x plus 2y plus 3z. 2 plus 6 is 8, minus 12 is minus 4. Minus 4 equals 0, or minus x plus 2y plus 3z equals 4. So that's the equation of the plane. Or if you like things to start with a plus sign, you could write this as x minus 2y minus 3z equals minus 4, but they're exactly the same equations, 1 multiplied by minus 1. Any questions about that? Okay. I'm doing some examples in the book, so this is example 5, part A. Part B is find the equation of the plane passing through the point P naught with the same coordinates 2, minus 3, 4, and perpendicular to the line given by the parametric equations x equals 3 plus 2t, y equal minus 4t, and z equals 1 minus 6t. So geometrically, here's what we have. We have a point P naught, and going through the point P naught, we have some line, L. And we want to find the plane through P naught perpendicular to the line L. So all we need to find is the direction vector of this line L. So the direction vector of the line is given by the coordinates of the coefficients of t, 2, -4, -6. That's going to be the normal vector of our line. So the equation of the plane becomes 2 times x minus 2 minus 4 times y minus -3 minus 6 times z minus 4 equals 0. It looks very similar to the equation we had a moment ago. In fact, if we divide this by -2, you get minus x minus 2 plus 2 times y plus 3 plus 3 times z minus 4 equals 0. It's exactly the same equation. So we get, in fact, the same plane. So that wasn't so hard. All right. Any questions so far? It's good every now and then to stop and review a bit. That's what we're doing. Okay. Well, remember, they teach you in school, and we saw today, that if you have any 2 points, that determines a line in the plane or in space. If you take any 3 points in space, that should determine a plane. 3 non-collinear points. Three points that do not lie on one line. Determine a plane. How do they do that? Well, suppose you have points P1, P2, and P3. Right? P1, P2, and P3. What do we need to define a plane? We need 1 point on the plane and a normal vector, a perpendicular vector. So I can choose any one of these 3 points as my point on the plane that I'm going to use in the construction of the equation of the plane. But how do I get a normal vector, a perpendicular vector? Well, if I take the vector from P1 to P2 and the vector from P1 to P3, P1, P2, the cross product with P1, P3 is orthogonal to or perpendicular to P1, P2, and P1, P3. That is, I have these vectors in my plane. The normal vector is perpendicular to both of them. How do I find something perpendicular to 2 vectors? You take the cross product. So suppose P1 has coordinates 2, -1, 3. P2 has coordinates 1, 4, 0. And P3 has coordinates 0, -1, 5. So the vector from P1 to P2 from here to here, if I subtract P2 minus P1, I get minus 1, 5, minus 3. And the vector from P1 to P3 has coordinates minus 2, 0, 2. So my normal vector is going to be P1, P2 cross product with P1, P3. I write this in determinant form. The coordinates of the first vector are minus 1, 5, minus 3. The coordinates of my second vector are minus 2, 0, 2. If I calculate that, this has determinant 10. This has determinant minus 2, minus 6, minus 8. So minus minus 8 is plus 8. And this has determinant minus minus 10, which is plus 10. Okay. So that's my normal vector. So the equation of the plane is 10 times x minus minus 1 plus 8 times y minus 5 plus 10 times z minus minus 3 equals 0, or 10x plus 8y plus 10z. This is 10 minus 40 is minus 30, plus 30 is minus 10. So I put this on the other side of the equation, equals 10. Let me just double check my arithmetic. This is 10 minus 40 is minus, there is it, minus 1, 5, minus 3. So this is 30 minus 40 is minus 10. Plus 10 is 0. Oh, sorry. My point is 2 minus 1, 3. So this is x minus 2, y minus minus 1, and z minus 3. So this is, let me just do this correct, the arithmetic correctly. 10x minus 20 plus 8y plus 8 plus 10z minus 30 equals 0. So 10x plus 8y plus 10z, this is minus 50 plus 8 minus 42 equals 0. So if I divide by 2, I get 5x plus 4y plus 5z minus 21 equals 0, or equals 21. So so again, if you want to see this legibly, and I always apologize for my writing, this is an example in section 13.5, which in my book is on page 851. This example is worked out nicely. Okay. So this brings us to section 13.6, which is today's lesson. Cylinders and quadric surfaces. So far in the plane, we've only seen lines, sorry, in 3 space, lines and planes. But there obviously are many, many, many other geometrical shapes. For example, there is the sphere. So if you take a point P naught in space and a certain distance r, you have the sphere of radius r with center at P naught, which is just the set of all points P such that the distance, the length of the vector from P naught to P is equal to r. It's all points P whose distance to the center P naught is equal to r. So that's one of the most basic geometrical shapes. There are many other things. Well, that's what a cylinder, talking about cylinders here. What does a cylinder look like? Suppose you have a circle and you have, say, a circle on the plane, and you just look at all the, you just lift it up in the z direction. You have a cylinder in 3 space. Let's see, what's one way to describe the cylinder? So suppose in the xy plane, we have the circle, x squared plus y squared equals 1, say, just the circle of radius 1. So in the xy plane, the circle is all points x, y, 0, where x squared plus y squared equals 1. Suppose I lift this circle up to a height z. Then this circle, lifted up to a height z, will be all points of the form x, y, z, where x squared plus y squared equals 1. And if you look at the set of all these points for all z, from minus infinity to plus infinity, that's just all circles above and below this circle in the plane. And this is an example of a cylinder. You have some geometrical figure which only involves x and y, and then you let the z coordinate run through all possible values. So it's like you're lifting your figure in the plane up and down to plus infinity and minus infinity. It sweeps out some nice surface, which is called a cylinder. That's what a cylinder is. Let me show you a parabolic cylinder. You know, in the xy plane, here's your parabola, y equal x squared. In 3-dimensional space, if this is x, this is y, and this is z, your parabola is sitting here. So this is all the points x, y, 0, where y equal x squared. That's just the parabola in the xy plane. If you look at all the points x, y, z, where y equals x squared, it's just this 3-dimensional surface. It's hard for me to draw it. Yes, it looks something like this. This is the way the drawing in the book looks like. This is your parabolic cylinder. A slice, what is sometimes called the XY trace, which is what you get by slice a plane through the cylinder. Just take a plane and cut it through the cylinder parallel to the XY plane. It will always cut out this parabola. So you have the so-called parabolic trace. That's all a cylinder is. So a cylinder is constructed or described by lifting a curve in one of the three coordinate planes. What are the coordinate planes? You have the XY plane. You have, let's see, this is X, this is Y, this is Z. This is the YZ plane. This is the XZ plane. You have the three coordinate planes. You draw some curve you have some curve in that coordinate plane, and then you just extend it parallel to that plane in all. Like if you're in the XY plane, you add a Z coordinate and you let Z run through all possible values, and that traces out a cylinder where the trace, the cut through that surface, is the same as the curve in the XY plane. It's just like if you look at this parabolic surface, every plane through this cuts it out in a parabola. If you look at this traditional cylinder, every plane cut through this cylinder cuts out a circle, and the circles are the same through this whole family of parallel planes. That's what a cylinder is. So it takes a while to get used to these geometrical constructions in space, but these are some of the basic ones. So basic one is a cylinder. A sphere is a basic one, not a cylinder. Sphere is not a cylinder. We have spheres and we have cylinders. Now, in general, if you have any equation, if you look at f of x, y, z equals 0, the set of all points that satisfy this equation describes a surface in 3 space. Like x squared plus y squared plus z squared equals r squared. The set of points that satisfy this equation, this describes a sphere of radius r. X squared plus y squared equals r squared describes a cylinder. In general, let's look at what are called quadric, which is short for quadratic, surfaces. So a quadratic equation in x, y, z has the following structure or form. So you can't have any monomial, any term with degree bigger than 2. So you might have ax squared plus by squared plus cz squared. So those have degree 2. Then you might have terms of degree 2 that involve two different variables. You might have xy, xz, yz. So maybe dxy, eyz, fyz. These are all the possible degree 2 terms. Then you might have terms of degree 1, x, y, and z, like gx plus hy plus iz, and you might have a constant term, j equals 0. So this humongous and rather unpleasant looking thing is a quadratic equation in 3 variables. That's a quadratic equation in 3 variables. And if you fix such a quadratic equation, you can ask for what are all the points x, y, and z that solve that equation. And the set of solutions x, y, z of such an equation is called a quadratic surface. And this includes the sphere and the cylinder and many, many other more complicated things. Now, the simplest are things that are generalizations of spheres called ellipsoids. So an ellipsoid, all these cross terms and linear terms are gone. An ellipsoid is something which has a solution, an equation of the form x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. That's the equation of an ellipsoid. Now, if you only had 2 variables, x squared over a squared plus y squared over b squared equals 1, that you're supposed to know from calculus is just an ellipse from minus a to a and minus b to b. So if there's no z term, this is the ellipse. And with the z term, you get some sort of surface that is called an ellipsoid. Now, let me just do an experiment for 1 minute and see whether I can succeed at this. Just one more second. Mhm. Okay. Um, so this is the equation of an ellipsoid. And suppose you're curious to see what it looks like. Now, for those of you who were fortunate enough to take Math 155 or 156 at Lehman, which is the calculus lab, and if in that lab you were fortunate enough to learn Maple, Maple can actually graph these three-dimensional figures for you. So I'm going to try to share the screen with a Maple. So let's see, can you see this Maple application right now? Is that visible?
Yeah.
Okay. So I opened this package called plots, and there's a command called implicit plot 3D. So this is going to graph something in 3D. So let's see, if there are some numbers in the book that I'll just follow the example in the book. Yeah. So in the book, one of the first examples of an ellipsoid it gives is x squared divided by not 3 squared, or 9. Let me just write it in the same form it's in the book. 3 squared, oops, squared, plus y squared over 4 squared plus z squared over 5 squared equals 1. There it is. Well, that's my ellipsoid. I can rotate it around so you can look at it in different ways. Kind of cool. Suppose I change these numbers to just A, B, oops, and C. So that's the general equation of an ellipsoid. And now I can take any numbers that I want for A, B, and C, like, I don't know, A equals 7, B equal, I don't know, 3, C equal 11. So for those parameters, that's my ellipsoid. See if I can make it. Let me make this 101. Yeah. Well, it looks kind of round because if you look at it, let me see. Let me do scaling constrained. Yeah. So, oops. I had 11 the first time. So now, yeah, that's what this ellipsoid looks like when it's drawn to scale. Yeah. Kind of interesting, right? Hmm, pretty good. So that in general is what an ellipsoid looks like. So that's an ellipsoid. That's one example of a quadric surface. What is another example? Second example is what the book calls an elliptic paraboloid. So an elliptic paraboloid is something which satisfies an equation like z equals x squared over a squared plus y squared over b squared. So let's look at the equation of that. Let's see what that looks like when I go to, and so the example in the book is with a equal 4 and b equal 2. So let me go back to my maple and try and plot that. So I'm using a command called implicit plot. And what I'm plotting is z equals x squared. Oops. Z equals x squared over a squared plus y squared over b squared. And I need some values for a and b. So suppose I let a equal 4 and b equal 2. Oops. Let me try something different. Oh, implicit plot 3D. I forgot the 3D. There we are. That's my, let me do this to scale. There we go. You look inside. It's kind of cool. If I change these parameters, let's make this, let's say 13 and it's 4. Looks different. Yeah. Anyway, if you are fortunate enough to know Maple, you can have a lot of fun graphing these things at home and seeing what they look like. So this is what is called an elliptic paraboloid. And there are some other strange things, and this is really the whole point of this section is just to look at pictures of curves that can come up later when we're doing vector calculus, um, and we need surfaces to be working on. So let's see. There are hyperboloids. So remember, a hyperbola typically looks like that in 2 dimensions. And in 3 space, we have hyperboloids of different kinds. A one-sheeted hyperboloid of one sheet looks like x squared over, here's an example, plus y squared over 9 minus z squared equals 1. All right. Let me see if I can draw that. So I want to do implicit plot in 3D. That's important. And my equation is x squared over 4 plus y squared over 9 minus z squared equal 1. Ooh, look at that. Now this is getting weird. Let's rotate that around. I want to do this to scale. Looks like that. That is our hyperboloid in one sheet. Second example is a hyperbolic paraboloid. So an example of this is an equation like z equals x squared minus y squared over 4. So instead of trying to draw this by hand, because there are pictures in the book and all that, but just to take advantage of the fact that I have some maple here. This is going to be x squared minus y squared over 4 equals z. Oh. This one is drawn to scale and not drawn to scale. It looks like that. Let's do one more example. So let me, this is the two-sheeted hyperboloid. So an example of this is given by the following example. Minus 16x squared minus 4y squared plus z squared plus 64x minus 80 equals 0. So let me try and get Maple to plot that. So I'm going to use implicit plot, and my equation is minus 16 x squared minus 4 y squared plus z squared plus 64 x minus 80 equals 0. Oh, well, that's a hyperboloid of two sheets. Well, clearly it has two sheets. Look it around. That's what this guy looks like. Huh. Kind of cool. Okay. All right. So 13.6, this chapter, the section that we're talking about has two subjects. Cylinders and quadric surfaces. So these are relatively easy to understand and draw, even by hand. These are hard to understand and draw by hand. Easy with Maple, or maybe any other algebra, computer algebra program you might have had in Math 155 or 156. But so I'm never going to ask you on an exam to draw or sketch a quadric surface. But when you're studying at home, you should look at the examples in the book. And if later in an integration problem or some vector calculus problem, you're working on a hyperboloid of two sheets, for example, you might want to go back and look at this section to see what the surfaces really look like. So the takeaway from today's lecture syllabus, or the lecture on the syllabus, which is section 13.6, is that there are various surfaces in three-dimensional space. They can be extraordinarily complicated. The simplest are cylinders, and the next simplest, which already are quite difficult, are these quadric surfaces that come from looking at solutions of quadratic equations in three variables. And to the extent you can look at these things and enjoy what they look like, that's great. We have one more topic, which is geometry in three space, which are two other coordinate systems, cylindrical coordinates and spherical coordinates. That's what we'll talk about next class, which is a week from today. And then the class after that, which again, I remind you, is Thursday of next week, we start actually doing vector calculus.
Professor, I have like another class like around like a Thursday, 11 to 1. So is it like can you switch it to another day?
Is it a Thursday class?
Yeah, it's a Thursday class.
Then it
Every
doesn't meet
Thursday.
next Thursday. Thursday, Lehman follows a Monday schedule. So no Thursday class will meet next Thursday. Only Monday classes will meet next Monday.
You said next Thursday, right?
Correct.
Oh, okay,
The
okay.
next Thursday, Lehman follows a Monday, CUNY, the whole university follows a Monday schedule. So a Monday lecture at 11 will take place next week only Thursday at 11. A lecture that normally meets Thursday at 11 next week will not meet Thursday at 11 because it's not a Thursday according to CUNY. There should be no conflict. In any case, every lecture we do is recorded and is on YouTube. So everything is there. But there should not be a conflict.
Okay, that's good. Okay.
All right. Anything else before we stop for the morning? Remind you, there's problem sessions which are underutilized. There's one tomorrow evening at 7 p.m. and I'm also going to have one on Friday late in the afternoon around 4:30, but I'll send out an email about that. So if you have questions about homework or anything in the lectures or anything in the book, that is a great time to log on and ask questions. And very often,
I have
one or two people there, and it's like a private tutoring session.
I'm not getting any emails about question session or anything.
Well, they're all posted. By email, I mean it's posted under announcements on Blackboard. So you're supposed to be checking the Blackboard site for your courses frequently, and that's where I post the times. Though what I said at the beginning of the semester is that there are routinely, unless there's something special, every Tuesday and Thursday evening at 7 o'clock, there's a Zoom problem session. And then there are additional ones that I schedule for people who can't make it then.
Okay, Professor. Okay.
Anything else? Again, enjoy your Valentine's Day and your weekend, and see you next Wednesday.
Thank you, Professor. Have a good one.
Thank you. You too. Bye, all.
Have a good one.